Hello, today we're going to be talking about building the RFLAN code for the BytePipe SDK from source. As you can see here, I have NextGen RF Design's GitHub page showing the BytePipe SDK repository. All the instructions for building the RFLAN are here. You can click on the RFLAN and you have building source, building HDL, building the RPU software, building a specific profile for your device. So if we follow these instructions, we can build the code. So let's start with the basics. We're going to use a Windows machine and Cygwin to build this. For more information on how to set up your machine, you can click here, the build environment. That will take you to what you need to install for Windows, Cygwin link, all the toolboxes for Cygwin, Vivado, Petalinux, and Vitis. So we'll go back here. So the first thing we're going to do is launch Cygwin, which I have up right here. And we're going to change to our directory. We're going to clone the repository, which I've already done. And then we're going to create a folder called Workspace. It can be anything. You can call it anything you want. You can put it anywhere you want. I like to call it Workspace. I like to put it at the top of the repo, and you will see that here in a second. So here is my C drive and the repository right here. I am going to open up Cygwin, and the first thing I'm going to do is change directories. Okay, and then I'm going to do BytePipe SDK. I'm going to make a directory called Workspace. And you can see over here it created a workspace. It's just an empty folder. The reason for this is I can delete this folder in the future and I will be losing all the build artifacts, but I will not be losing any source code. All the source code that's used in building is all still up here in source. If you modify any of the source code that is in any of the projects that are built in Workspace, it gets modified up here in the source folder. So deleting Workspace in the future, you won't lose any of your source changes. All you'll lose is the build artifacts. So we're going to use Vivado and Vitis. Both are Xilinx tools. So we need to export those to our Cygwin environment. You can set up Cygwin to have them permanently exported. I like to do it every time I open Cygwin. That way I can use different versions of Vivado for different projects. I'm going to type in Control R because I've done it in the past to search for my path. But really what you need to do is type in this to export your Vitis path. I have installed in the D drive, but this is what you need to type in, and you can see building HDL, we're exporting Vivado. So actually what I should be doing is changing this to Vivado. Because we're going to build the HDL first. Now you can check to make sure that worked by just typing in which Vivado, and you can see it found it. Okay, so now we're going to make the HDL. The HDL can be created from the source files with just one script. So if I copy this, put that in there. Now this is going to, we can watch our folder over here. This is going to download source files that are not part of the SDK repo. And it's going to build all the libraries and IP associated with the HDL. And then finally it will build the HDL. So let's go ahead and do that. We do need to type in which device we're using. I am using this 3CG. So we'll type that in, we'll hit enter. So the first thing it's doing is building the ADRV 9001 programmable logic, which is part of the SDK. It started by creating an RFLAN folder over here, which is what we're building. The ADRV, which is currently being built, is an IP that's used within the RFLAN. That's why it's a separate folder. It's a separate set of IP independent of the RFLAN. So first it's building the ADRV HDL, and you can see it created a IP module. Now it's building the DMAs from analog devices, which it has to download from GitHub. And that's a separate set of IPs, so you can see in here, it's building that. So it has to build, I think, 3 or 4 different pieces of IP from the analog devices repository. And you can see it is doing that now. The IP doesn't take too long to build, so we'll just watch it do its thing here. Once we get to the RFLAN, that does take about 10 minutes to build, and we can speed through that. But it built 4 libraries that are used as part of the DMA, and now it's building the actual DMA IP. Okay, so now it's building the RFLAN programmable logic. And we can see in here it now has created in the RFLAN folder a Vivado folder. This Vivado folder will have the RFLAN HDL project, and the RFLAN will be using the IP outside of it. This does take about 10 minutes or so, so I will speed up while this is building. Okay, so the HDL build has finished. You can see here in our workspace folder under the RFLAN project, we have a XSA file. This is a zip folder containing all the information about the HDL build, including the bitstream and other files used to create the software. It is labeled based on the part. You can build uh, multiple programmable logic versions for different parts that the BytePipe supports. Make sure you match this with the version of BytePipe that you have based on the processor. So what we can do next is we can open up Vivado. So I've opened Vivado 2021.1 and I will open the RFLAN project, which is in the workspace RFLAN Vivado folder. I can show you that once this loads. What I did there was I clicked on the project was remembered in my favorites, but you can see here is the project file. So that's basically what I just opened. Okay, so it is finished. We've met timing. Um, you can see the resource utilization. Um, let's see here. Let's open the block diagram. Okay, so here's the block diagram, which just shows the major programmable logic components. We have the DMAs over here. We have an AXI interconnect, a couple of them, the CPU, and then here is the ADRV 9002 programmable logic. The RFLAN project simply connects the ADRV 9002 to the DMAs, which then allows the processor to stream data to and from the ADRV for evaluation purposes. The top level module right here is in Verilog, and you can see it has all of the ADRV I/O, and then it instantiates the block diagram, which we had over here. If we open up the implementation report, we can look at how about report utilization. So the RFLAN you saw used 10% maybe or 15% of the logic resources. A lot of those resources are tied up in the DMAs and the interconnects, the AXI interconnects. This module itself is very small. So if you're going to take this design and tweak it, maybe add a modem in between the DMA and the ADRV 9002, or maybe you can get rid of the DMAs altogether and use a FIFO to interface to the CPU. Whatever you're going to do, you have potential for reducing resources significantly by reducing the DMAs. And you'll see that in the utilization report too, as it opens here. You will notice that the debug, the integrated logic analyzers are included, and I can show you that in a second. But you see they're referred to up here, but which also consumes a fair amount of resources, although not too bad. But you can go through and look at the resources here. If we change it to percentages, forget how we changed that. Well, anyways, we'll look here and we can see the ADR v9002 resources, and then the interconnects actually use the most resources, and then the DMAs. So these are the main components. You can look at the resource report here, power report. You can see here, including the processors, we're at about 1.675 watts. One thing I will show you, whoops, open block diagram, is in here you can configure the ADR v9002. I have configured it to use the integrated logic analyzers for each RX1 and RX2, TX1 and TX2, each stream port. And then these swap diff flags allow you to swap differential pair for easier PCB routing. So the BytePipe itself swaps several diff pair from the P to the N, and that's what these flags are for. The default is based on the BytePipe configuration. All of the documentation for the RFLAN HDL and the ADR v9002 HDL is online. If we go to RFLAN and we look at the programmable logic, you can see there's some documentation around it here, which also takes us to the ADR-V programmable logic documentation, which is here, and then it goes into more depth about the transmitter and the receiver programmable logic. Here is a picture of that ILA, integrated logic analyzer, and showing some of the timings associated with the ADR-V control signals. So I encourage you to read up on this. It does touch on the configuration that we just talked about. And then also describes all the registers that are in the programmable logic. Those are accessed through the AXI interface, which is interconnected to the CPU. So that completes the tutorial on building the HDL. The next video will be building the software for the RFLAN. Thanks for watching.